let me solve one problem in this lecture that will make use of everything that we have learned. The problem that I am solving is from Griffiths, chapter 9, problem 36. This is also similar to a problem in Jackson's book, which is problem number 7.2. I will take one part of it from there, and then this Zangwill's book. This is related to problem 17.17. So, here is the problem. Light of angular frequency omega passes from medium 1, let us say refractive index N1, through a slab of thickness D and refractive index N2 into a medium of refractive index N3. Find the transmission coefficient. So, what this problem says is, here is medium N2, there is light coming in from medium N1, goes through medium 2 and passes here, and there is some reflected light also, or the incidence is normal.
I want to know how much this light is going out. So, let us see what this problem encompasses. There is light coming in normally. Let this be surface 1, let the other one be surface 2. Let the distance between the two be d as given in the problem. The refractive index in the first medium is N1, and the second one is N2, third one is N3. As light hits the first medium, it will get reflected. So, there is an I coming in, and there will be some ER, and part will be transmitted. So, let us say this is E transmitted in medium 2. As it hits the other surface, part will be reflected, let us say E R2, and some part will be transmitted, let us call it ET.
And this will happen again and again and again, it will keep happening. So, finally, what is happening through all this is, in this medium, there is this light which is coming in, and then the reflected light gets components from this multiple reflections. And I am going to replace all this by one big ray of ER, and the EI is coming in. Similarly, inside the medium, there are these E transmitted which are multiple. I am again going to replace them by one ET 1, ET 2 I am writing. And there is this reflected part here also, which is also made up of many, and I am calling this E R2. And finally, there is this transmitted ray. So, we are saying these are the final amplitudes, and now we apply the boundary conditions. To apply those, I have one surface at x equals 0, the other one is at x equals d, and I have to have two sets of boundary conditions, one on the x equals 0 boundary, one on x equals d boundary. So, on the x equals 0 boundary, I have EI, ER going out, then I have E transmitted to ER 2. So, the equation is going to be EI 0, the amplitude that is understood, plus ER is going to be E T2 plus E R2. That is my equation number 1. The other equation would be for the magnetic field, which says that E I over V 1 minus E R over V 1 is equal to E t 2 over V 2 minus E R 2 over V 2. And I replace this by refractive index, then I am going to get N 1 E I minus E R is equal to N 2 E t 2 minus E R 2. That is my equation number 2. These are very simple equations because we have been doing it at x equals 0. So, e raised to I k x part goes away. Now, we will do this for the second surface, which is at x equals d, and that is where I am going to have E t 2 e raised to I k 2 d plus E r 2 e raised to I the minus sign k 2 d is going to be equal to E transmitted e raised to I k 3 d. That is my equation number 3. And the fourth equation is going to be for the magnetic field, and that will give me N 2 E t 2 e raised to I k 2 d minus E r 2 e raised to minus I k 2 d equals N 3 E t e raised to I k 3 d. That is my equation number 4. I have 4 equations, and how many unknowns do I have? I have 4 unknowns also. I have 4 equations and 4 unknowns. What are those unknowns? E r, E t 2, E r 2 and E t, and we are interested in E t over E incident. So, I will eliminate the other parts. So, let me write these 4 equations once more. I have E I plus E r equals E t 2 plus E r 2, that is number 1. Then I have N 1 E I minus E r equals N 2 E t 2 minus E r 2, equation number 2. Then I have E t 2 e raised to I k 2 d plus E r 2 e raised to minus I k 2 d equals E t e raised to I k 3 d. That is equation number 3. And finally, I have the fourth equation from the magnetic boundary condition matching, and that will be N 2 E t 2 e raised to I k 2 d minus E r 2 e raised to minus I k 2 d equals E t N 3 e raised to I k 3 d. That is my equation 4. K 2, which is omega over V 2, is N 2 omega over C. K 3 is omega over V 3, which is N 3 omega over C. So, I know K 1, K 2 also. And what am I trying to calculate? The transmission coefficient, which is going to be 1/2 V 3 epsilon 3 mod E t square divided by 1/2 V 1 epsilon 1 mod E I square, which I can write using n square equals epsilon as n 3 over n 1 mod E t over E I square. I am writing this formula directly in terms of mod, but I again want to remind you that using the complex notation, right, we had this S time averaged as 1/2 E cross B star divided by mu 0, and that is what I am using, right, which is time average of real part of, this is time average of real part of E cross B over mu 0. So, this all gives you this. So, N3, N1, everything is known. All I want to calculate is ET in terms of EI, and I have these 4 equations. So, we can quickly do this. From the third and the fourth equation, I get E T2 equals N2 plus N3 over 2 N2 ET e raised to I K3 minus K2 D. And I also get E R2 equals N2 minus N3 over 2 N2 ET e raised to I K3 plus K2 D. And I need to plug these in into equation 1 and 2. And equation 1 and 2, what I need is E T2 plus E R2 and E T2 minus E R2. And these come out to be, I will put them together, E T divided by 2 and 2 e raised to I K3 D, that will come out common, and inside I get e raised to
minus I K2 D N2 plus N3 plus or minus N2 minus N3 e raised to I K2 D. So, you found those, both of these. So, I can write therefore, from equation 1, which is E I plus E R equals E T2 plus E R2. So, this comes out to be E T over 2 N2 e raised to I K3 D, and I can open up this exponential and write this as
2 N2 cosine of K2 D minus 2 I N3 sine of K2 D. And similarly, for the other equation, which was E I minus E R, I can get N1 E I minus E R is equal to E T over 2 N2, that is common, e raised to I K3 D is common, and I get minus 2 I N2 sine K2 D plus 2 N3 cosine of K2 D. The rest of the task is very easy. All I need to do is eliminate ER, and I go through the manipulations, and that gives me 2 Ni EI 0 equals Et e raised to I K3 D times N1 cosine K2 D plus N3 cosine K2 D minus I N1 N3 over N2 sine K2 D minus I N2 sine of K2 D. I am giving you these middle steps so that when you work it out, you see that you are not making an error. And this then leads to E I 0 over E t equals e raised to I K3 D over 2 N1, N1 plus N2, N1 plus N3 cosine K2 D minus I N1 N3 plus N2 square over N2 sine K2 D. And remember what I am after? I am after N1 over N2 mod E I 0 over E t square, which will be 1 over t, and then I can write t. So, this immediately gives you n 1 over n, sorry, it should be n 3, because I am talking about the transmission in medium 3, n 1 over n 3 mod E I 0 over E t square as equal to e raised to I k 3 d mod is 1, so it will become 1 over 4 n 1 square times n 1 on top will become n 1, then n 3, and inside I will have n 1 plus n 3 whole square cosine square k 2 d plus n 1 n 3 plus n 2 square divided by n 2 square sine square k 2 d. You can now simplify this and get t equal to 4 n 1 n 3 divided by n 1 plus n 3 square plus n 1 square minus n 2 square times n 3 square minus n 2 square divided by n 2 square sine square k 2 d. That is the transmission coefficient. Now, I am going to go over to problem 7.2 b Jackson using this expression. That problem says that in this medium where you have n 2, n 1 and n 3, suppose there is some optical instrument on this side and you want all the light coming from here to pass through, no reflection, then what should be n 2 and d? This you given that is passing in the air. So, there is some n 1, there is some n 2 and n 3 is 1, and therefore, the transmission coefficient that we just calculated becomes 4 n 1 divided by n 1 plus 1 square minus n 1 square minus n 2 square, n 2 square minus 1 divided by n 2 square sine square omega over c times n 2 d. And we want that t be 1, and this means I want that n 1 plus 1 square plus n 1 square minus n 2 square with a minus sign times n 2 square minus 1 divided by n 2 square times sine square omega n 2 d over c be equal to 4 n 1. You can bring 4 n 1 to the other side and write this as n 1 minus 1 square, therefore, should be equal to n 1 square minus n 2 square, n 2 square minus 1 divided by n 2 square sine square w n 2 d over c. Our left hand side is positive, and therefore, this implies that n 2 should be greater than 1, but it should be less than n 1. Then only the right hand side can be positive. So, that is point number 1. Point number 2 is that sine square omega n 2 d over c will always be less than or equal to 1. And therefore, n1 square minus n2 square, n2 square minus 1 divided by n2 square should be greater than or equal to n1 minus 1 square. Then only this will be satisfied. So, that is point number 2. And it is point number 2 that tells us what n2 square should be. So, let us work that out. So, I have n1 square minus n2 square, n2 square minus 1 divided by n2 square should be greater than or equal to n1 minus 1 whole square, or n1 square n2 square minus n1 square minus n2 raised to 4 plus n2 square should be greater than or equal to n1 square n2 square plus n2 square minus 2 n1 n2 square. Now, I am going to cut terms. This term cancels with this one, n2 square also gets cancelled, and I get, by flipping the sign, that n1 square plus n2 raised to 4 should be less than or equal to 2 n1 n2 square. This gives me n1 minus n2 square should be less than or equal to 0. Now, left hand side is perfect square. So, this cannot be less than 0. This implies the only possibility is that n1 minus n2 square be 0 or n2 be equal to square root of n1. Putting this back into the equation, that was n1 minus 1 square equals n1 square minus n2 square, n2 minus 1 divided by n2 square sine square n2 omega d over c gives me, substituting the value of n2 equals root n1, n1 square minus n1 times n1 minus 1 divided by n1 sine square root n1 omega d over c. Then I have this whole thing cancelling this, or sine n2 omega d over c equals 1, or n2 omega d over c equals pi by 2, and therefore, the thickness should be equal to c pi over 2 n2 omega. With this thickness and n2 being square root of n1, I will have no reflection. So, what we have determined is that if I have a system where normal incidence plane wave is coming from the left with refractive index n1 falling in a medium of thickness d and then going to medium n3 equals 1, if n2 equals root n1 and omega n2 d over c is equal to pi by 2, then I have no reflection and all wave passes through. Let us just write this condition of thickness in terms of lambda and see what it means. So, I have omega n2 d over c, which is 2 pi times the frequency n2 d over c equals pi by 2. So, I have 2 pi n2 f over c d equals pi by 2. This implies 2d over lambda is equal to 1/2. So, 2d is equal to lambda by 2. So, by the time this wave comes back, it has traveled a distance of lambda by 2. That means reflected waves from the first and the second boundary interfere. This is a kind of way of understanding this. There is a corresponding phenomena that happens in quantum mechanics also. In quantum mechanics, what happens is, if you have an electron or a particle coming in some potential, it goes through a different potential and goes to the same potential again. So, what one is saying is that I have a potential, then there is a well, and then it is going out. The outside again could be a different potential. So, the possibility is also that there is a well, and then there is a different potential, and particle is coming in with some energy. This lambda in the 3 places is going to be different, and sometimes the particle just passes through. So, this is no back scattering, the particle just passes through, right. So, that will also happen when this lambda 2 is such that 2d over lambda 2 is 1/2. So, you see, this studying this wave phenomena in electromagnetic theory, and particularly seeing this reflection and all these things, right, has a one-to-one correspondence with whatever happens with Schrodinger waves. So, it gives you that very nice way of understanding quantum mechanics also. So, just conclude this lecture here by saying that we have solved a problem involving 3 medium and an EM wave incident normally on their parallel interfaces. Thank you.